Hi, everyone. Welcome to our talk today. It's titled All You Need is Consistent Promotions. So today I will be presenting, I'm Kanchana. I'll be presenting with my colleague, Anneya, on this really interesting topic. It's given us sleepless nights and we've tried to figure this out for many days. So I hope you find it interesting as well. So a little bit about ourselves. So Anneya has been a data scientist at Kinaxis since 2018. She has a master's in astrophysics from St. Mary's. She loves running, crocheting, and dogs. I know for a fact that she can crochet some incredible things overnight, so she's pretty good at it. Interests include demand forecasting and optimization problems, and this talk is really in her forte. I'm Kanchana. I'm the director of data science at Kinaxis. I got my PhD in computer science from NC State. I also teach part-time at the University of Toronto and Ryerson University. I'm mom to a very, very energetic 2-year-old and very passionate about productizing machine learning solutions and bringing it to market and seeing how it can benefit end users and customers alike. All right. So the agenda for today is as follows. I'll kind of talk a little bit about who we are at Kinaxis, what we do, and I'll introduce the problem of promotional planning in retail. Anneya is going to take it forward, dive into all of the issues we face when we are building machine learning solutions for this problem, as well as a solution that we've come up with one of the most intricate problems that we've faced so far in this journey. So Kinaxis has been around for many years now, since 1984, almost as old as I am. It's a platform for integrated business planning, as well as digital supply chain. It's in over 75 countries, has more than 10,000 users, and Gartner often rates us as one of the leaders in the space. We're also in many different industries, from aerospace to automotive to consumer, packaged goods to retail to high tech to industrial to life sciences, and some of the top, folks in these industries happen to be our customers. So a little bit about the Kinaxis AI system itself. We have a pretty mature, I would say, a machine learning system. It starts off with a data platform, which is our ingestion ETL platform that helps us work with both customer data as well as external dynamic signals like flu and weather and so on. We also have a very mature machine learning as a service platform that helps us orchestrate, schedule, scale, run, monitor all of our machine learning jobs. And the crux of it all is, of course, our machine learning solution itself, which has all of the common culprits. We have a good feature engineering system, a sophisticated forecasting system, a sophisticated evaluation system, which I think is key for any machine learning system. So all of the training, distributed model training, hyperparameter tuning, and all of that. And finally, of course, we also have an optimization engine on top of it all, which is useful for some of our use cases. Like, for example, we have a flyer planning solution where we need to decide what products go on a flyer in what slot and how it can work across many different weeks. And that's essentially a fantastic optimization problem to solve. We're also quite active in a lot of our academic research initiatives. We partner a lot with academia to publish work. I would say we really do it reasonably often, but of course we do it when we have something interesting to talk about. The latest one being the one in the Canadian AI conference earlier this year. We are also quite popular in the conference circuits, speaking at the International Symposium of Forecasting, the Toronto Machine Learning Summit, conferences such as the Strata Data Conference, Canadian Data Science conferences, and so on. And also our team spans across Toronto and Ottawa. So we have two very large machine learning teams working on these interesting solutions. All right, so now to get to the crux of it all, which is the problem we're trying to solve, which is the promotional planning in retail. So exactly what is this problem, right? So as a category manager, and a category manager, for those of you who don't know, is just someone in a retailer who's responsible for the welfare of certain products, right? So that person is responsible for deciding what promotion to put on this product, How often do you run a promotion? When do you run a promotion? How do you maximize margin? How do you keep sales constant? How do you account for things like vendor funding? So it's a really interesting job, but they're also very responsible for the welfare of these SKUs. And often they have these different levers to play with where they can decide, what promotion to put a product on, what kind of discount to provide. Do they put a product on the front page of a flyer, the back page of a flyer? Do they have to run it in a specific region? Do they have to run the promotion across the board? And are there specific groups they need to target? Like, is it a seniors promotion? Is it a student promotion, and so on? So they have a lot of these different levers that they can play with, and they often have to do this job every few weeks because, if you go to a store, you see things are always on promotion, right? So it's something that they are constantly working on, right? And of course, and just to step back, one of the top trends in retail for 2021 has been stated to be exactly this problem, where they talk about algorithmic merchandising optimization, which enables retailers to more precisely determine the items that need to be displayed in stock. It also determines how items should be priced and promoted. So bringing in machine learning into the space is actually a huge win across the board. And that's exactly where we are in the space that we are. So we have a product called Optimize that essentially help the category managers do that, where they have all of these levers, they can play around with these levers and see what scenario makes sense for them for a particular product, and then choose a scenario that actually helps them satisfy all of their business needs. But at the crux of it all, of course, it's a simple machine learning problem. I say simple, but it's actually quite complex. Simple in the sense of, you know what you're predicting. You have to predict the total units. A given SKU will sell. There are some features that go in. There are certain promotions that are encoded in the model. We can tweak and play around with these levers and then see what the output looks like, and then compare these outputs and say, okay, one output is probably better than the other. For example, in this case, let's say you're trying the same SKU A on 2 different promotions, buy one, get one free, and price cut 50%. And okay, looks like price cut 50% seems to be a bit better, because it gives a little bit more sales as well as more uplift, and okay, maybe that's the scenario you need to go with, right? So far, I haven't described anything that's rocket science, right? It seems like a simple machine learning forecasting problem. You have features, toggle with the features, you get some outputs, and then you compare those outputs. Of course, if it was that simple, I wouldn't be here. So let's take a step back to understand what the crux of the problem is. So the law of demand states that all else being equal, okay, given that you can kind of keep everything else constant, the quantity purchased varies inversely with price. What that means is, like, giving everything else is the same. If the same product's on a 20% discount versus a 30% discount, of course, I would buy the product. I would buy the product that's on the 30% discount, right? The exact same product. Why would I choose to pay more money for the same product, right? Like, when I can get it for less money. Okay, just logical, right? And so you would expect this nice smooth curve that you see on the screen, where as the discount increases, you'll expect that the quantity increases beautifully, right? If this were true, we're done, right? We can build a model, we're okay. But of course, that's really not the case. When you start building machine learning models that are trained from historical data and try to mimic this behavior, you see some really strange patterns like you see on the right here, where somehow putting a product on 0% discount causes a higher sales than when it's on 20% discount. And then somehow around like 50% discount, there's a dip that's lower than when it's on 40% discount. So these are kind of strange scenarios where, if you present this to the end user, they'll be confused because, when a category manager is planning, he's assuming that given everything else is constant, if you put something on a 20% discount, at the very least, it should sell as much, if not more, than something that's on a 0% discount, right? So that's the problem that we're trying to tackle today. And I'll hand it over to Anneya, who's going to walk us through some details on exactly why this can happen, as well as a solution for how we can tackle it.
Okay, thanks, Kanchana. So first of all, why are these curves we're looking at so much uglier than what we'd expect? There are a bunch of reasons possible, but fundamentally, we're looking at these forecasts produced by the models. And assuming we've done our jobs correctly in setting up these models and training them, most of the problems come from the training data. The main issue is that in the real world, our clients are interested in looking at predictions for promotions that are run with like a 1% discount or a 90% discount, but they're really not interested in running promotions like this. So we're looking at actual historical data that only samples a small subset of the possible values we're interested in. Retailers are typically reluctant to run experiments like this because running a bad promotion is risky. They could lose money and lose the trust of their own customers. Other big problems are that good promotions lead to stockouts, and when retailers aren't able to meet the demand of their customers, we end up looking at censored observations. They also intentionally censor the demand by putting redemption limits on really good promotions, like 1 coupon per household or something, which makes our historical data even worse. Also, there might be instances where demand for a product is affected by promotions on other similar products, like if Pepsi and Coke are competing and one of them is on sale, but the other one is more on sale, we might not measure the realistic demand in isolation. So the issue we're trying to resolve is that in our UI, users can create a promotion with a specific value and receive an on-demand forecast. When they change the degree of a discount, they expect to see an intuitive increase or decrease in the forecast. So to be clear, we're keeping all of the model features for our ML models constant. We're looking at forecasts for, say, some product on some day in some store, just changing the percentage discount. We expect consistent increases in the forecast with consistent increases in the discount. So we've come up with a procedure to make our UI behave more intuitively, regardless of the ML model that underlies these predictions. We're looking for, instead of returning this rocky looking set of predictions, something that conforms to some expectations, like what we see in the green line on the right. And to put that concretely, we're looking for a smooth curve that is monotonic across the range of values of interest, and produces smooth changes in the forecast when we make any adjustment in the degree of the discount. The procedure by which we do that is to put the predictions through an isotonic regression, which results in a piecewise linear fit to the outputs of the model. And then we pass that result into a monotonic interpolator that smooths out that result and makes sure that we get that consistent increase with small adjustments. So looking at the first step, the isotonic regression takes a set of blue points that in this case would be the output of our model at various values of the discount and fits the red piecewise curve to it. So we end up with flat portions of the curve, but we can guarantee that it's monotonic across the range of values. So then we want to achieve the smoothness by passing that piecewise linear fit through a monotonic interpolator. So typical polynomial interpolation can introduce deviations from monotonicity even if the points that are input are monotonic. There are a few types of interpolation methods that do preserve monotonicity, and one of them is the p-chip interpolation, which is what we use here. So to summarize that entire procedure, the first step is to identify the driver of the promotion, which is the independent variable which we expect to have a monotonic effect on the overall demand. So we then sample the range of values of interest for that driver and generate forecasts at each of those. We then apply monotonic regression to the forecasted demand as a function of that driver. To get our first step, we then identify locations in that curve where we see a jump in value. So we're throwing out all of the flat portions and we pass that through the monotonic interpolator to get our final smooth curve. So because these are the outputs of our machine learning model, which we've trained on historical data to be as accurate as possible, we expect that a good adjustment changes that as little as possible. So we make a few checks to make sure that we haven't changed things too much, and we're not actually just going to be returning terrible predictions at this point. So we look at the amount adjusted, which we define as the relative L1 distance between the original points and the adjustment, and we expect that to be as small as possible if we've done a good job. We also look at the interval where we don't see any changes in the prediction when we change the forecast driver, the promotion driver, and we want that to be as little of the range as possible. So that said, let's look at a few examples. So here's an example where the quality of adjustments is good. So the blue line represents the output of our model, and green is the result of our adjustments. We see only small changes made, and the non-responsive zone is pretty small. Typically, retailers don't actually run discounts greater than, say, 50%. And especially if we're using models that don't extrapolate well, like tree-based models, it's not a terrible thing for us to see something flat at high discounts. So something worse is if we see a dead interval at low values and significant changes between the output of the model and the smooth result. And something very, very bad might look like this, where the output of the model was actually, monotonic in the wrong direction, say. And this would be a strong indication that there's something more going on in the training data. And we'd want to revisit that and see if there are confounding factors that we're not including in the model, and check whether there are additional features we could add to explain this, or if there's something else going on. So we've implemented this for promotions that have a single driver, like percentage discount, where it's straightforward to generate predictions out of a range of values and run the fit. Clearly, this increases the time to return something to the user. We need to sample various points and generate, if we're looking at percentage discount, and we want to sample, say, like 100 different values of percentage discount and then smooth it out, we need to generate 100 more predictions than we would have otherwise and then perform the smoothing. But we can cache those results, and the actual interpolation and isotonic regression aren't that expensive. So at this point, this is working out okay, and it's not too expensive to run. If for more complicated types of promotions where we have like buy two, get some percentage off, we haven't implemented something yet, but that will definitely be more costly to run. So other options to make the forecast more intuitive would be to encourage retailers to run more experiments and improve their training data. Conversely, we could do this directly in models by using models that support monotonic constraints in cases where we can represent promotions as single features and build the isotonicity right into the result. That would, of course, be dependent on using those specific types of models, and we would need to write a solution for everything. But definitely different options to consider as we go forward. Thank you very much. We'll take any questions now, and please feel free to connect with us on LinkedIn.
Yeah, and we're also hiring. So anybody who wants to work in the space, it's not just our data science team. We have a machine learning as a service team, as I talked about. We have a data platform team, and we're kind of hiring for different teams across the board. So definitely reach out to us on LinkedIn, or definitely feel free to apply online as well. So thank you very much for listening to us.